Good morning, everyone. I just want to greet everybody online and in person. At the Institute of Earth Physics and Space Science, I am still learning the name that we took a few years ago. I spent 40 years in the Geodynamic and Geophysical Research Institute. Well, this meeting is hosted by István, Kovács and Professor Sierd Cloetingh. Please follow the instructions. There are many conferences and meetings are organized at the Institute in connection with the General Assembly of the European Geoscience Union. As you know, the Institute is playing a leading role in space science in Hungary. At the beginning of May, we organized a big space science conference, and also the Institute will host the workshop of the IAGA meeting, International Association of Geomagnetism and Aeronomy in the middle of May. Well, I asked István Kovács to officially open this meeting, and I wish you to stay and school discussion. Thank you very much.
Thank you very much, Viktor, for the welcoming speech. I'm especially delighted to have Professor Sierd Cloetingh in our community again. And I think this is a very special moment because Sierd won the distinguished professorship from the Hungarian Academy of Sciences for the third time, which is probably a kind of record, but it didn't just happen in vain. But there was, I think, a very fruitful and productive scientific performance behind that. And the present meeting is also a follow-up of this collaboration, and Sierd encouraged us to have a meeting or a conference on the energy resources and also the geo-hazards, and we will touch on some aspects of this. And I'm also extremely delighted to have in our community Professor Gábor Tari, the Chief Geologist of UNV, and also Károly Német, well-known volcanologist presently from Saudi Arabia in the scene. And I hope we will have a very productive conference and having great discussions, both from the on-site and also from the online participants who will have a chance to ask in the chat window. And just to keep the schedule, I would like to ask Sierd Cloetingh to give his opening speech. So, Sierd, please.
Good morning, everybody. Many thanks, Viktor, for hosting us here in the beautiful institute, and big thank you to István to organizing the session of today. It's always a great pleasure to be here, and what I like to do this morning is to make with you a brief journey from the deep earth to the surface, And in doing so, I like also to present to you some of the work that we have been doing here in Geoprom and subsequently in other places. And that's work that is basically a follow-up of some things that we started 2 years ago here with István and Alexander Koptev, and more recently Alessio Lavecchia, also one of the speakers here today, also was involved in that. What I like to do today is basically go first a little bit into the deep earth, talk a little bit about heterogeneity in the upper mantle and in the lithosphere, and then basically explore the interaction of plumes in the upper mantle and the overlying lithosphere. And what I like to demonstrate here is that we have been pretty much involved in what István is calling the plume factory, and in particular in terms of the different expressions of different types of plumes. Well, heterogeneity is a fact of life, and this tomographic image, this slice in the upper mantle between depths of 200 and 100 kilometers, is a result of the seismology group in Utrecht, showing us basically the expression of the mega plume underlying Iceland and major parts of the mid-Atlantic rift system in red, but also what is very interesting, side lobes of this plume, which go all the way till southern Norway and the western part of Britain. And that's interesting because southern Norway is an area where we have a lot of topography, mountains, far away from the plate boundaries, so they should not be there. And in the western part of Britain, we have recent volcanic activity also in an interplate setting. All these things have been quite enigmatic to explain, but it looks like that a major cause for this is the hot upper mantle under these areas. That's very interesting. At the same time, we have also a lot of heterogeneity in the mechanical properties of the lithosphere. You can see this from this plot of the effective elastic thickness, which is a parameter characterizing lithospheric strength. And what you can see in the different colors is areas in brown, which are the areas where we have a weak lithosphere with a low value of the effective elastic thickness. And this is, of course, in the young parts of the oceans, but also in the areas such as the Alpine Mediterranean area. And you see in blue and pink, you see areas where we have a high strength corresponding to a high value of the effective elastic thickness, primarily in the continental shields, like the Canadian shield, the Siberian shield, or Western Australia. So heterogeneity basically occurs at many different levels. And that's also clear when you look into the thickness of the continental crust in the European domain. And this is work that we carried out some years ago with Magdalena Tesauro, who is now an associate professor in Trieste. And what you can see here in dark blue on the left-hand side is basically the areas where we have a very small thickness of the crust. And of course, no surprise, that's in the oceanic areas and in the Western Mediterranean. And in red, you see areas where we have a very high value of the crustal thickness. And that is very much, of course, to the eastern part of the Trans-European Structure Zone. And here, of course, very thick crust here in Finland. You see a reduction in the crustal thickness in the Pannonian Basin, but also in the European Cenozoic rift system, which is essentially made up of the Rhine Rift and the Rhone Rift. So also here we have heterogeneity quite clearly expressed. When I was a student entering university, I was told, well, we have heterogeneity in the crust, but at deeper levels, everything is the same. Well, if you look to the tomography pictures that I showed you before, that's not exactly the case, but it's also something that we can see if we look to the regional component of residual mental gravity anomalies, and this is obtained with satellite data. And also here, basically, you sample heterogeneity below the crust in the upper mantle. And what you can see here are values where we have a mass deficit here in red, and that's in the Western Mediterranean, but also in the European Cenozoic rift system, and also in the Pannonian Basin. And you see areas in blue where we have excess mass, and that's for the Adriatic indentor, but also clearly visible here in the Trans-European suture zone. So heterogeneity is certainly not limited to what we obtain in the crust. This type of information has also been used by us to construct strength maps for different continents, starting with Europe, but also later for North America and other parts of the world. What you see here in different colors is a integrated strength for the lithosphere, where in red you see the areas where we have low strength, and in blue you see the areas where we have high strength. And well, what is very clear, let's say that the Trans-European suture zone is again an area where we have a big contrast between the strong lithosphere in the Russian platform and the weaker lithosphere in Central and Western Europe. And you see a lot of red here in the Pannonian area, but also clearly here demonstrated in the domain of the European Cenozoic rift system. What is also shown here is the distribution of interplate and plate boundary seismicity. And if you look to this map, you see that one of the premises of the first days of plate tectonic, that the plates, their interiors, that they were rigid, is certainly not valid for our part of the world. There's a lot of seismicity in the interior of in the interplate setting in Europe. And what you can clearly see is that the earthquakes, the interplate earthquakes, they like very much the red areas, the weak lithosphere, but they even like more the areas where we have a contrast between red and blue. That means a contrast in strength from weak lithosphere to strong lithosphere. So also this type of approach helps us a little bit to understand more where are the areas which are prone to interplate deformation. We can also explore this type of things by a combination of numerical and analog modeling. And here you see basically a setting where we have taken as a starting point the strength profiles for continental lithosphere, and where we play a little bit with the mechanical coupling between the mantle part and the crustal part of the lithosphere. And that has a big impact on the style of collisional tectonics. You see here an analog model with different assumptions. You see here basically the mantle part of the lithosphere. You see here the crustal part, and you see a contrast here between the downgoing plate and the overriding plate. And here you don't have that type of contrast. And what you can see in the mode of collision, that has a big impact on the style of thrusting in the collisional zone. Here you see a propagation of deformation this direction, and here you see basically completely different style of basin development, and with major implications also in terms of the differences in the overlying topography. And that's interesting. It tells us that the rheological stratification of the continental lithosphere has a direct impact on what's going on the surface. Well, not far from here, we have a fascinating problem where a lot of discussion has been on the base of seismic tomography carried out by the AJH group in Zurich, where basically the inference was that this area in the Alps is basically an area where we have a flip in the polarity of the downgoing plate, going here in a southward direction and here in a northward direction. And in between, basically, is an area which is a little bit complex, where we have the transition. And this was exactly the area where in the beginning of this century, the deep seismic Transalp line was obtained, which was a little bit problematic in terms of interpretation, because they were basically shooting this line exactly in the most complex area where we have this, according to the recent results in tomography, where we have this flip in the polarity. Well, what we have done a few years ago was to investigate with analog modeling what are the consequences of this change in the polarity of the downgoing plate, moving here in a northward direction on the eastern segment and here in the southward direction. And you can see such a transition in the polarity clearly has a big impact on the style of surface deformation and the style of topography. So this type of modeling helps also with the interpretation, basically, of what we can obtain with seismic data, whether it's seismic reflection data or data from seismic tomography. In the last few years, a lot of attention has been given to the impact of processes in the upper mantle and the surface, also to the impact of flow in the upper mantle below the lithosphere on the surface. And the terminology for that, in terms of what is this mantle flow doing on the surface, is the word dynamic topography. And well, maps have been constructed, like this one shown here on this slide, where basically different experiments, numerical experiments have been made for different assumptions. And basically what you see here in blue are the areas where we have a negative dynamic topography, and in red are the areas where we have a positive one. Well, if you look to this map, then you see a lot of red here in the western part, which is very nice in terms of the Atlas Mountains, the anomalous topography of Iberia. It has always been an enigma because the average elevation of Iberia is higher than the average elevation of Switzerland. It's intraplate, so it's a little bit difficult to explain. But you see also red here in the trans-European, European Cenozoic rift system, which is characterized by subsidence and not by uplift. And you see also some red here in the Pannonian Basin area. Well, the situation is changing if you are not using a global model for crystal thickness, which is a rather coarse model, but if you take a better constrained model for the crystal thickness, in this case, the model that I showed you a few minutes ago, made by Magdalena Tesauro, and that is the EU Crust 07 model, constrained by all the available seismic data available at that time for Europe. And what you can see is a big change made by taking a more accurate model. In this case, essentially, we also obtain here positive topography for Anatolia, which is a very well-studied plateau, where the previous simulation basically did not give us that result. It leads to some further refinement, but also some problems with dynamic topography by only looking at the mantle processes remain, like what I mentioned before, the features predicted for the European Cenozoic rift system, where in reality we see subsidence and not uplift. What is important here in this approach, that all the causal mechanisms are attributed to the upper mantle. There is no attention here for what's going on in the lithosphere itself. There's no attention for the role of, for example, interplate stresses. There is no attention for lower crustal flow, for example. A lot of processes that we know which are important and which we have to take into account when, for example, we do basin modeling for continental lithosphere. So the point is that when we look at topography, we cannot simply attribute it all to mental processes or all to crustal processes. We have to attribute it to a combination of these. And that was basically the message of a paper that I published a few years ago with Bilal Haq in Science, where we made the point that inherited landscapes, often the result of an interaction of surface processes and processes in the deep earth, are important to also basically control past sea level change. And of course, for that, we should not forget the sedimentary record in the basins. Another important issue is that different processes can give very similar expressions at the surface. And that's basically the message of this slide here. You see here, on the top, you see basically an interaction of a plume and the overlying lithosphere. And this is a continental lithosphere. And what you can basically see here is a differential topography coming up with uplift alternating with subsidence. And this is a completely different process. This is lithospheric folding set up by plate tectonic forces propagated from the convergence zone into the foreland, giving also differential vertical motions, and basically with a signature which is very similar to the signature that we obtain when we have an interaction of a plume with an overlying mantle. And at first sight, that was pretty surprising to us. How can it be that two completely different processes give a similar expression? Well, if you think about it, you realize that is simply the result of the mechanical filter, which is imposed by the lithosphere itself, which has a rheological stratification, in many cases with a upper crust mechanically decoupled from the mantle part of the lithosphere. And whether we attack this lithosphere from below or from the side is not really that much different in terms of the expression at the surface. It's the same filter. But it illustrates again how important it is to take into account insights we have on the mechanical structure of the lithosphere when we talk about the effect of different processes. And Europe is a good place for that, because Europe has been very well studied by geophysical and geological methods since a long time. And if you look to the slide on the left-hand side, you see basically the ratio of crustal and lithospheric strength, where in red, the most of the strength is in the crust, and in blue, most of the strength is in the mantle. And of course, if you look to oceanic lithosphere, where the role of the crust is very, very small, then you are not surprised to see here dark blue. And again, it shows also that heterogeneity in the strength of the lithosphere is a fact of life. Well, if we then start with the plume and we attack this lithosphere, then we get what I mentioned before, very much differential motions at the surface. We also induce lower crustal flow and also, as a byproduct, down thrusting of the mantle lithosphere in the surrounding areas. And that's a very interesting result. When we did this work some years ago, then basically Evgeny Burov was very much interested in the interaction of the lithosphere and the plume, with a focus on what's happening directly on top of this plume. And of course, this is the surface topography that got the major attention. But basically, to me, it was very interesting to see this down thrusting on the side, because down thrusting of lithosphere in other words, subduction, it's always been an enigma, how to initiate that. I did my PhD thesis on that many years ago. It was basically a nice paper in Nature. It showed that aging of oceanic lithosphere in itself will not lead to initiation of subduction. And I was very happy to leave that topic because it was a negative result. And then from a completely different angle, basically looking at plume lithosphere interaction, I saw the downthrusting taking place here in a completely unexpected way. So we decided to move a little bit further on this. And well, since that time, basically I got a little bit more involved in the plume factory. And more recently in joint work with István and Alexander and Lavecchia, we have published a paper in EPSL where we basically looked very much at the effect of small plumes on the overlying lithosphere, the secondary plumes. Because you all know, let's say, we have the primary ones, which come all the way from the core mantle boundary, like the mega plume under Iceland. But this mantle transition zone is also very interesting in terms of the role it has in launching from this area the secondary plumes. And so we called this this paper fingerprinting secondary plumes. Don't have the illusion that you basically listening here to Sherlock Holmes, because the point is here that we see different expressions of the secondary plumes if we go to the areas where they have been detected. And for that, we took some examples located in the European Cenozoic rift system here, which I mentioned before already, and here from Southeast Asia. And let me show you some examples. Here we see the secondary plume under the Eifel area in interplate Europe, not far from the Dutch border in northwestern Germany, where we have a very small plume with a radius of around 100 kilometers at most, going all the way up to the surface, and very enigmatic because this is in the middle of Europe. Recent volcanic activity, our predecessors have seen this volcanic activity, and again, how to explain it. Another small plume here under the Baikal Rift, and here under the Hainan plume in Southeast Asia. And here you see a very interesting observation. You see here a big plume coming up, and then it's being split into a number of the secondary plumes at shallower levels. So it's a very interesting feature. And this is basically an interplate setting, but it also occurs on top of downgoing slabs, like here in this examples. And the mode of penetration is quite different. This is clearly a kind of arrowhead type of penetration, whereas in the previous case, under the Eifel, this is basically a finger-shaped penetration. And the key question is, what is the reason for that? Well, what we have been doing is to set up some numerical models. Here you see a piece of the lithosphere and overlying an upper mantle. And you see here a small plume coming up. Radius is only 50 kilometers, so a very small one. Yeah. When these things were first found in Western Europe, it was really an enigma, this small plumes. They were called baby plumes because they are so small that basically they look completely different, let's say, from the big ones, like under Iceland. And we were in the beginning a little bit surprised that they were only found in Western Europe. So was it because our seismologists are better than the people who do seismology in other parts of the world, or was it just accident, or is the mantle under Europe so special that it only happened here? But soon afterwards, a lot of these things were also found in other parts of the world, in particular in Southeast Asia. So what we did was to do a little bit of numerical modeling. examining basically the role of the density anomalies inside the plume, corresponding with the contrast with the mantle around it, but also the role of weakness zones in the overlying lithosphere, and also the role of tectonic stresses. And what I'm going to show you is just a few examples of the results, more details in the EPSL paper that we published recently. And what you see here in this simulation are essentially a number of cases where you see here on top a mushroom type of penetration. You see here the plume is rising up. Here it's getting closer to the surface, and here it starts to interact, but it is not penetrating the overlying lithosphere. Here you see an arrowhead mode of penetration. You see here the plume coming up, starting to penetrate the lithosphere, is going partly in it, but is really not reaching the surface. And here, the mode of penetration that we see in the Eiffel, finger-shaped penetration. Here, the time evolution, and you see this thing's moving very quickly. It's really in no time this thing is reaching the surface. And what is the difference essentially between these three cases is the density difference with the surrounding mantle. Here we have a big difference. Here, intermediate density difference, and here pretty small one. That's primarily making the difference. And how do you increase the density difference? Well, make the plume hydrous. So not only a thermal perturbation, but also a hydrous plume. And here we were, of course, very much influenced by István and by Alessio, petrologists, who basically told us, well, you did so far a lot of work on plumes, but it's not only thermal. So I said, okay, let's try it out. And the basic story is essentially that in order to get the finger-shaped penetration, you have to invoke, and that's the red mode here, you have to invoke either a big density difference or, let's say, a very wide area with weak lithosphere overlying the plume. And the best is a combination. Then, of course, you can also look a little bit into the role of the tectonic forces. And by the moment, let's say, you impose stresses on this lithosphere that is attacked by a plume, you basically promote the development of finger-shaped interaction of the plume with the lithosphere. So it gives a little bit of an insight in terms of the different modes. And let's have a little comparison between the different cases, modeled and observed. Again, this is the situation where we have basically an arrowhead penetration here in the model, and this is what we observe for this case here very nicely. This is Eiffel, finger-shaped penetration, yeah, and this is a different case where essentially you see the plume has interacted with the lithosphere. There's some down thrusting on the side, but the thing is already spreading here. So this is in a different phase. So it's not only a difference, let's say, in terms of the spatial pattern, but there's also a temporal effect here. But everything happens in a very short time. Okay, so far enough about the baby plumes or the secondary plumes. Let's go back to the big ones. And again, let's have, of course, the inspiration here from the Northern Atlantic. The Northern Atlantic is flanked by rifted continental margins. And these continental margins, also called passive margins, are not so passive as you might think, because if you look to a typical cross-section for such a continental margin, like the Norwegian continental margin, you see a lot of volcanic underplating. And that's shown here in red. And if you look essentially to this thing on a global scale, you see in red the areas where the rifted continental margins have a volcanic character, and that's why they're called volcanic rifted margins. And more than half of the rifted margins in the world are of this nature. Something that we did not realize in the early days of plate tectonics. So volcanic activity is not only something, let's say, you have to expect in convergence settings or in rift zones, but also, let's say, in what traditionally have been called passive continental margins. Well, as usual, there's a lot of debate on mechanisms, whether it's basically for plume lithosphere interactions or for rifting. And the traditional way to look at it was basically to say, well, we have two modes of rifting. One mode is what we call passive rifting, and that is basically just due to plate tectonic forces. And the other mode is active rifting, where all the damage comes from below a plume, so to say. Well, what is interesting, if you look to the different observations, then you see also that there are cases which are a little bit in between, which we call semi-active or semi-passive. And the difference is essentially in the expression near the surface and closer to the surface. And for all these types, the active mode, the passive mode, the semi-passive and the semi-active, we have plenty of examples. So what Alexander Koptev and myself have been doing in a recent paper was come up with a new classification for rifting and rifted continental margins. And what I'm going to show you is basically some examples for the Southern Atlantic. And that's basically what you can see here. The Southern Atlantic has a rich variety in rifted margins, big differences if you go from the north to the center here and to the south. And that's basically what you can see here. The southern part is very nicely associated with seaward dipping reflectors, very nice underplating, the whole thing. So classical case for active rifting. Then we move to the far north, Brazilian margin here. Typical case for passive rifting. There is, of course, some upwelling here as a result of the rifting, but not as the cause. And otherwise, very nice structures in the overlying crust, but no underplating, nothing like that. And then we go to the central part, semi-passive. You can see basically there is some underplating, but it is not so dramatic as what we see in terms of the expression of volcanic activity as what you see more in the south. So even within one ocean basin, you can have basically very important transitions in the style of rifting. And that's something that is, in our view, important. So here you see them all the way from active to semi-active, semi-passive, and pure passive. Well, the intention here is not to make things more complex, but to obtain a little bit more insight in different expressions of the different processes, and to avoid the situation where we just focus on end members, because pure active rifting and pure passive rifting are clearly end members in the whole spectrum. Let's move back to the north, and let me very briefly talk a few minutes about another feature which was not basically under consideration in the early days of plate tectonics, and that is the occurrence of compressional domes in the oceanic lithosphere in rifted margin settings. As we all know, this system has been created by continental breakup. That's all very nice, but there is also some very interesting topography in the seafloor shown here in brown. And these are compressional structures, and these are basically tertiary structures. And on the seismic section, they look like this. Very nice, what we call basin inversion, compressional structures, but in a setting which we in general treat as basically a rifted margin setting. And this is a little bit enigmatic to explain. Initially, we thought about, let's say, the role of interplate stresses in doing this, but it's a little bit difficult to explain why exactly here. And what is also interesting is that they occur most times pretty close to a fracture zone. And to examine this, Alexander Koptev, who will speak later in the morning, and myself had a closer look at it and followed the propagation of some hotspots in the area, and also took into account the role of the fracture zones in terms of what this upwelling in the mantle is doing at the surface. And our proposition basically was that what we see here in this compressional domes has to do with leakage of hot material from the side lobes of the plume in the northern Atlantic along the fracture zones. And if you look to the topographic expression, then you basically see here structures which at first sight you might say, well, that's typically, let's say, compressional deformation set up by plate tectonic forces. But in this case, it comes from a completely different cause. So again, different processes can give very similar expressions. And you need different types of data to sort it out. Well, let me finish here with a few other results from the plume factory. And that is basically the issue of plume-induced subduction initiation. And also this work was, of course, inspired by observations, like here from the Caucasus region, where we have upwelling here of the upper mantle, surrounded by downthrusting of continental lithosphere. And Iberia, I already mentioned that Iberia is an interplate setting with an anomalous topography, underlain by a hot upper mantle here, but also surrounded by areas where we see downthrusting. And what we did was first look at the issue of plume lithosphere interaction in an ocean setting, and this work also was carried out by the ATH group of Tadas. And we came basically to similar results, and you see basically that what's happening here, the plume comes up, is penetrating the lithosphere, and after a while you see here this downthrusting of the surrounding area. But if you do this for a continental lithosphere, it's even more interesting, because then you see the importance of the thermotectonic age of the overlying lithosphere in the whole process. This is a lithosphere with a thermotectonic age of 60 million years, so a relatively young lithosphere. This is a one of 150 million years. This one, 300 million years, and this is a very old one, 1,000 million years. And you see in all cases, the plume is capable to result in downthrusting of the mantle part of the overlying lithosphere. But the most spectacular case is essentially this situation, where I have pretty old lithosphere here on the side, and here in between a weaker part of the lithosphere. That's basically the area where I can very nicely induce pretty deep going initiation of continental lithosphere subduction. What I also can see here in the case of an old continental lithosphere, that the plume has an effect, but is not capable really to make it closer to the surface, simply because the overlying lithosphere is too strong and is providing a mechanical barrier. So again, also here, the role of the rheology in the whole process is crucial, and we should not forget that. We should basically, when we combine all these processes, we should not basically underuse the information that we have on the crust and the lithosphere itself. let me finish here with a little cartoon, essentially making the point that sometimes it's easier to start the downthrusting of the lithosphere or initiation of subduction under the continent, but it can also migrate. And from this position, it even can migrate to the ocean-continent boundary and start to initiate a downthrusting of oceanic lithospheres. So again, something to further explore, and that's exactly what we will do in the coming phase, not only for thermal plumes, but also for hydrous plumes. So I like to leave it here. Just a few conclusions. Mantle lithosphere interactions, they can operate at different scales. The thermo-mechanical structure of the lithosphere, the tectonic regime, and contrast between rising plumes and upper mantle are quite important. And secondary plumes are in general of hydrous nature with different expressions as mushroom-shaped, arrowheads, and finger-shaped modes of penetration in the lithosphere. And we have nice examples of all of these things if we have a closer look at the lithosphere and upper mantle in different parts of the world. I like to leave it here. Thanks for your attention.
That was very much precision, so we are absolutely on time. And I ask first the audience whether there is any question for the presentation.
Just to get the ball rolling, questions from my mind, I'm sure that everybody else's mind. One thing which was very interesting for me is new subdivision of the passive, semi-passive, semi-active. And on the semi-passive, so we showed just for a moment high density, lower crustal bodies in that model. And I was wondering whether you could extend on that context of those bodies. It's a very small question among many others, but of course, the reason why I'm disagree.
Yeah. Well, what is important, let's say, is apart from, let's say, the mode of interaction at the beginning, there's also a little bit of temporal change in the whole thing, and that's something we explored in the past already. For the Pannonian Basin, for example, the transition where you start with passive rifting and at a certain moment the thing gets going and you end up with active rifting. Well, what is the key point here is again to realize that dependent on the density contrast, thing can change, and that's interesting because the initial classification of volcanic rifted margins was very much in terms of seabed dipping reflectors. Carl Heinz found these things and then volcanic rifted margins. The observation on the deeper level often came later. And what is interesting is that seabed dipping reflectors in itself is not really the only thing that you can say this is purely active rifting. So it also depends very much on the type of lithosphere and that is on top of it, on the hydrous nature of the plume, the size of the plume, and if you want to, let's say, have more detailed information, this mega paper of Alexander Koptev, myself, and Todd Ehlers in Geophysical Journal reports on the results of hundreds of simulations, where all these things basically are looked at in more detail. These cartoons are essentially to illustrate a little bit in terms of the main differences, but there are many more subtle differences also when these plumes are migrating into the adjacent continent. Yeah. There's a question on the back. Yeah. These are the most difficult ones.
No. I try to very simply. Question is the crustal, lower crustal flow. Just think about, the metallurgical side. I'm coming from the material side.
Yeah.
So it's a little bit hard to understand for me. So just a few few clues this to understand better the lower crustal flow.
Yeah. This is an issue. I still remember when we made the strength maps for Europe. We started with that. We had to assume, let's say, different lithologies. And I still remember my discussions with Jacques Touret, my colleague in petrology at that time. I said, "What should we put there?" You know. And well, he could not give me really a specific answer. Of course, we realized that the presence of weak lower crust or stronger lower crust depends also on the location. And of course, in this strength map, we took that into account. So we looked basically for different assumptions, and we made also, let's say, different sets of models, assuming a weak lower crust and a strong lower crust. In the context of, let's say, an uprising plume with a mantle anomaly, a temperature anomaly, you weaken the overlying crust, and you first, when you get basically closer to the surface, you run into the lower crust, and you can initiate this lower crustal flow, in particular if you come from below, and in particular if you are in a rift setting. So the first time that we looked at this was very much in terms of the evolution of rift shoulders, where essentially this lower crustal flow was more important than we expected before. It doesn't mean that lower crustal flow, let's say, is always occurring, and I frankly don't expect this to occur, let's say, in the Russian platform, for example. But in a situation like the Rhine Rift, it's pretty likely, because also whether we work with plumes or with plate tectonic forces, of course, the ideal place to get things done is in an area where we have already a pre-existing lithosphere, which is weaker than its surrounding. So it's a little bit related to that point, but I take your point very much. Let's say that lower crust can also be, let's say, of a different nature. And if you look to the strength profiles we have been publishing, you see also that we compare a case where we put diorite in the lower crust versus diabase, where we basically take a wet lower crust and a dry lower crust. So all these things have been looked at in the past. And but in the setting that I discussed so far, let's say it is reasonable to assume that in these cases, a lower crust, which is relatively weak, is more likely than one that is relatively strong.
If there is no online question, I just check it here. See if we have online question. No, there is no online question.
Okay.
Then thank you very much for
pleasure.
the excellent presentation and for the in-depth answers. And now we are moving to the next presentation, which will be an online presentation given by Alexander Koptev from Potsdam, from the GFZ. Alexander is, let's say, an exceptional young scientist with many international awards, and let's say one of the inheritors of Yevgeny Burov, and he's also working together with Sierd for a long time, and it's our very great pleasure to have him in our community. And Alexander, please give your presentation on the East African rift system. Thanks. Thank you, Alexander.
Hello, everybody. Thank István for this invitation and for this introduction. I will speak today about geodynamic modeling of plume-induced rifting and continental breakup, mostly focusing on application for East African rift system. Here you can see the general plan of my presentation. I will start with some general aspects of so-called intermediate scale geodynamic modeling. Then I will show some applications for East African rift system. This is, let's say, the core of my presentation today. Then I will show some results of coupled geodynamic and geomorphological modeling I have, and I finish with a few words about perspective toward fully coupled mantle lithosphere atmosphere modeling approach. So let's start with general aspects of intermediate scale geodynamic modeling. So what I mean when I say about intermediate scale modeling, it is well known that there are a lot of different global models of mantle convections, which are able to reproduce many interesting features observed in our planet, including global observations of seismic tomography, and also it also possible to reproduce the first order zone of localization of deformation corresponding to boundaries of lithospheric plates. But when we would like to explore more detailed structures which we observe in geology of this or that region, we, for example, like this transition between wide and narrow rifts, we have to consider a different scale model. For example, this a good example of high resolution modeling approach, but in this case, naturally, to have high resolution of experiments to resolve all these nice structures to demonstrate difference between distributed and localized deformation, for example. Naturally, usually in these experiments, they have to significantly reduce the vertical dimension of experiments. So in this case, it is just several tens of kilometers. Intermediate scale geodynamic models, they should from one side keep significant depths, so it should include at least the entire upper mantle and probably even part of lower mantle. But another side, they should also include sufficiently high resolution to allow resolving deformation at the crustal and lithospheric level. Of course, this requires a lot of computational resources, but a few years ago, such kind of models are possible. As Sierd has already told in presentation, apart from why high resolution is important, as mentioned Sierd in his presentation, actually rheological structure of the varying lithosphere is extremely important for the in the crust and in the lithosphere, and therefore our high resolution should be sufficiently high not only to resolve the main faults in the crust, but also to resolve these rheological structures, this rheological stratification, which could be different depending, for example, on the age of continental lithosphere. To keep things simpler, I just would like to illustrate here that depending on this important question on the composition of lower crust and also depending on the temperature distribution in the crust and in the lithosphere, we will have different degrees of rheological coupling. What does it mean? It means degree of coupling between brittle layer in the upper crust and brittle layer in the lower crust. For example, in this case of strong lower crust and relatively cold geotherm, we will have no ductile layers at all. And in this case, we will speak about strong coupling. But once our crust is compositionally weak or extremely warm, we will have weak coupling or, in contrast, strong decoupling. So this rheological structure, as Sierd already mentioned many times in his very interesting presentation today, is very, very important for the resulting style of system behavior. And previously in the literature, these two very famous terms on so-called jelly sandwich and creme brulee, corresponding to, let's say, this two end members case of rheological stratification of the lithosphere. And what is important is that this rheological stratification is important not only for fault or deformation distributions, but also for distribution of surface topography. As Sierd mentioned again in his presentation, this rheologically stratified lithosphere plays a role of filter, which permits to have very differential surface topography response to, for example, emplacement of mantle plume or to external extension or compression. But in case if we assume simplified model of monolayer viscous lithosphere, as usually done in low resolution global models, our surface response will be quite simple, but actually it is not what we usually observe in nature. Actually, this is why it is extremely important to implement into the models this multi-layer brittle viscous lithosphere. And again, these models, which have been already shown by Sierd, it was already explored in 2D, is mantle plume rising from the bottom of the upper plate, upper mantle, sorry. So first we have normal topography, domal topography uplift above plume, but then topography response is much more complex. So this was explored in details in 2D in these studies by Sierd and his co-author Evgeny Burov. And what I did in my studies, I have used in general similar model setting, but in 3D. So we have here these two layers of continental crust, lithospheric mantle, sublithospheric mantle, mantle plume at the bottom of the upper mantle, and also so-called sticky air at the surface, just to have a possibility to simulate free surface deformation. And here you can see evolution of this reference model. So here you can see 3D view where you see this body of mantle plume rising towards the bottom of the lithosphere. Here you can see the vertical cross section where you can see, of course, penetration of the plume. You see that in this level of vertical cross section, the plume is even penetrated into the lowermost part of the lithosphere. But in the crust, at the level of the crust, we have this nice brittle deformation in the upper part of the crust, but lower part of the crust is mostly subjected to ductile deformations. And then normally plume should not quickly penetrate into the lithosphere if the temperature of the plume of reasonable value and if the overlying lithosphere is sufficiently strong. We have such mushroom-like behavior of the plume head, and at the surface we can observe gradual opening of this rift valley. And in the topography, you can see that, again, we start with symmetrical domal uplift. This time we can see it in 3D. Then this uplift area is intersected by rift valley, which starts to open gradually while keeping these so-called rift shoulders at the surface. But what is interesting is that after several tens of million years of such relatively slow extension, we can get some transition from this wide rift deformation zone to relatively narrow one. And this narrow zone is accompanied by localized uplift of mantle plume and decompressional melting inside of body of mantle plume. And final stage of this model, it is actually total rupture of the lithosphere and transition from rifting to oceanic spreading stage. And what I would like to highlight here is that when we test different geotherms or different temperatures at the MOHO in our models, we naturally have different degree of this rheological decoupling. So here this lithosphere is decoupled, but you see that this viscous layer is much thinner than, for example, in this case of extremely hot geotherm, extremely high value of MOHO temperature. And you see that paradoxically, In case of hotter crustal geotherm and in presence of mantle plume and in the context of relatively slow tectonic extension, we have narrower zone of deformation at the surface than in case of, let's say, colder geotherm and less decoupled lithosphere, where we have deformation much more distributed. Why I call these results not intuitive? Because it is well known from previous models of purely passive extension and passive and relatively fast extension. You see that here it is value of extension is of order of 1 centimeter per year. Here we usually have different results. We have that once structure is lithosphere is coupled, we would have narrow rift, but once lithosphere warm and rheologically decoupled, we would expect, in contrast, wide distribution of deformation. We will have wide rifting. So you see that in case of extremely slow extension and in presence of the mantle plume, we have a totally opposite tendency. And I will show you in application to nature that sometimes this, let's say, not intuitive and not traditional case could better fit the natural observations. So now I move to application to the East African rift system. This is a well-known system which extends from Afar Triple Junction toward Lake Malawi from north to south. And in the central part of the East African rift system, we have two contrasting branches. One eastern branch is very hot and very magmatic, but in western branch, most of deformation occurs amagmatically. And if we look at this image, this seismotomographic image, you see that at the level of the lower mantle and even upper mantle, lower part of upper mantle and lower mantle, we have strong thermal anomaly, which rise toward this eastern branch segment, but also there are some relatively small anomalies below western branch, and it is not totally clear if they are connected with this source in the lower mantle or not. So actually this question, how many mantle plumes are in below East African rift system, is still open, but it is no doubt that there are some thermal anomalies, and we need to consider this system of this rift system in the context of interaction of the lithosphere with mantle plume. And here you can see that actually there are also, in this case, we have no homogeneous lithosphere. We have strong and thick Tanzanian craton surrounded by, let's say, normal lithosphere formed by Proterozoic mobile belts. And actually, it is also clear that these rift branches, they prefer to develop inside of this relatively thin lithosphere, while the craton remains almost undeformed. So to explore this situation, I have implemented this anomaly in terms of thickness of the lithosphere into my previous model. So I just, again, have lithosphere, have mantle plume below, but I just added this body corresponding to Tanzanian craton. And to make things more interesting, I have slightly shifted initial location of the plume with respect to center of this cartonic body. And you see that what we can observe in this case. So here it is, again, dimensions of my model. So it is still very wide and very deep to satisfy this criterion of intermediate scale model. Okay, so you see that mantle plume uplifted, but in this case, instead to spread laterally below the lithosphere, as it was in the case of homogeneous lithosphere, it is deflected by craton keel towards the relatively thin lithosphere nearby. And you see that expectedly, the deformations are also localized not in the thick, cold, and strong craton, but in the lithosphere nearby, just above the head of deflected head of of the plume. So by this model, we can also reproduce asymmetrical distribution of magmatism, because naturally we have decompressional melting only in one side of the craton. And what is also important and interesting is that here we also can observe this along axis variations in the width of the rift, because here naturally in the central of the plume head, we have the strongest thermal impact, and in accordance with my previous results and previous tendencies shown with homogeneous models, that warmer lithosphere results in narrower rift, but towards the north and towards the south, where the impact of this thermal impact of the plume head is not so strong anymore, we have significantly wider zone of deformation. And actually such a long strike variation in the width of rift, it is exactly what we observe along eastern branch of East African rift system, where we have transition from white Turkana rift toward Kenyan rift just above presumable head of Kenyan plume. And then we have again North Tanzanian divergent zone, which is relatively wide to the south. But again, if we look at the result of this simple model and to this map of observed distribution of deformation, it is clear that our model reproduces very successfully this western branch, this eastern branch, both in terms of magmatic asymmetry and also in terms of some along strike with rift variations. But still there is a problem what we should do with this western branch, which is naturally not reproduced in this simple model. So how can we localize this amagmatic deformation in opposite side of the craton? The simplest solution, it will be just introduce some weak zone. For example, I have introduced this feature in terms of lower viscosity of at the lower crust level, or we can just implement second mantle plume. I told you that nobody knows exactly how many plumes there are in below East African rift system. So probably this small body of plume would also help us to localize deformations. And you see that actually both assumptions are working. You see that this weak zone leads to localization of absolutely amagmatic deformation along western side of the craton. And here in this case, in more natural way, we also have localization below this smaller plume, but given the size of plume is small, we would expect, of course, much less intensive magmatic activity there. And third opportunity to reproduce similar situation will be following. So in our first experiment, we have big mantle plume, which was slightly shifted to one side of the craton, and this resulted in a total deflection of the plume head to one side of the craton. But if we make this plume a little bit bigger, and if we make this shift significantly smaller, what we could expect? We could expect actually this asymmetrical distribution of one single plume body, which would actually result in similar distribution of plumes. And actually this experiment, it is view from bottom, it is top view. And you see that indeed we have this asymmetrical splitting of the plume head. We have more magmatism and more deformation in one side, and less localized deformations. Not less localized, but less intensive deformation here. And of course, we would expect less magmatism there. So in this study, I have proposed these three possible scenarios to explain this asymmetrical dual system around Tanzanian craton with one single plume and weak zone, or with two independent plumes of different sizes, or with one single plume, which was split asymmetrically by cratonic body in between. But if we again look at the system in nature, we can see that the situation could be even more complex. First of all, we have also this southern prolongation of western branch, which is called Lake Malawi Rift, and also apart from this Magvelo block located to southwest of it. To model this more complex situation, I have increased the size of my model box, and I have implemented second symmetrical body of craton, and I also put mantle plume somewhere in between of Tanzanian craton with small variations of its initial location. And then I also modified the configuration of Tanzanian craton to fit it better with its actual configuration. And I have tested a lot of experiments to show that actually very small variations in initial location of the plume with respect to this the structural heterogeneities in the lithosphere would result in significantly different, after all, distribution of plume material and more important, in different distribution of deformation at the surface, because you see that in certain cases we have almost no deformation here in the western branch, but in other cases these deformations are very well pronounced. So this model, which I consider, let's say, the best fit from all performed, you can see that in this case we can indeed reproduce by one single mantle plume, and with these two lithospheric heterogeneities, not only strain rate, but also topography distribution, which fit observations, the first order observations. So it is eastern, western, and branches, and also Malawi Rift to south. But again, if we look more close to observations, we can see that we have also this Rukwa Rift, which are located exactly between Tanzanian craton and Bangvelo block, and has not north-south, but this oblique orientation. And another important aspect is that here we have not just narrow rift, but we have this wide zone of deformation corresponding to North Tanzanian divergence zone. And here in model we have deformation, but in nature there are no deformations. So make this to overcome these discrepancies, I have implemented one more small block corresponding to this Masai block here. And also I have changed not only thickness of the lithosphere below cratons, but I have also changed the composition of the cratonic blocks. As discussed before, this crust in, let's say, a very old lithosphere will be indeed stronger. It will correspond to mafic rocks rheology rather than just to simple one layer wet quartzite or felsic rocks compositions. Therefore, once we introduce one more lithospheric heterogeneity and change not only thickness but also composition of the crust inside of the craton, we can actually get distribution of deformations which fit very well observations. So you see that in this case, this fault do not want to penetrate into strong crust of craton, but prefer to be oriented obliquely. And also because of this strong Masai block, strong not only in terms of thickness of the lithosphere, but also due to presence of mafic layer in the crust, we can also reproduce this distributed deformation in North Tanzanian divergence zone. So the general conclusion is that to fit better observations, of course, we need to implement some complexities in our experiment, but even with a relatively simple model setups, including only this first order heterogeneities at the level of the lithosphere, all deformations and all this complex rift system could be reproduced with implementation of only one single plume, which could be just asymmetrically deflected by this lithospheric heterogeneity. So this is general conclusion of all this long series of experiments from very simple to this relatively complex. And then to finish this African stuff, I would like to move a little bit to north towards this so-called Afar triple junction, where our East African rift system in the form of main Ethiopian rift meet Gulf of Aden and Red Sea spreading axis. Actually, now we have already real spreading there, which was preceding, of course, this phase of rifting. And according to this concept proposed many years ago in Paris, formation of this triple junction could be related by this asymmetrical slab pool applied to Afro-Arabian plate due to gradual closure of Neo-Tethys Ocean here. So you see that 65 million years it was subduction everywhere, but 30 million years we had collision here in Beatles area, but still subduction here. So as a result, we would expect that slab pool here will be much stronger than pool here. And actually this asymmetry in boundary, this external tectonic velocities would result in this counterclockwise rotation of Arabian plate. And it is important to note that this onset of collision in western segment of Tethys subduction zone is coincide in time with possible emplacement of so-called Afar mantle plume here, which in my opinion is independent mantle plume with respect to this Kenyan plume, which was emplaced a little bit shifted to south due to relatively shifted to south due to this movement of Afro-Arabian plate to north. Okay, so to imitate this situation, I then just, of course, removed cartonic block from my model, but I combined this east-west extension applied in all my experiments with this, let's say, northward oriented traction, which gradually increase from western part of the model to eastern part of the model, just to imitate this gradual transition on this southern boundary of Eurasian plate. And again, here I have performed a lot of different experiments just to test different combination of values of this east-west extension and this northward traction. You see that eastward this extension was always constant, but value of traction was changed from minimum to maximum value, just again to imitate this this lateral transition. And you see that naturally, once we have dominance of northward traction, we have drifting zones oriented from east to west. In contrast, when we have small northward component but strong east-west oriented extension, our rift is oriented from north to south, just like in our western and eastern and western branches in the central part of East African system. But when the value of extension and traction are comparable, we can actually reproduce this triple junction and even relative orientation of main axis of localized deformation, which roughly corresponds to all main structures observed in nature. So here it is Red Sea, Gulf of Aden, Ethiopian rift, and even its prolongation to south corresponding to Kenya rift, or we call it eastern branch of central part of East African system. Okay, so I finish here with my African models, and then I would like to say a few words about different slightly different approach where I combined geodynamic models with geomorphological modeling. It is well known, and of course, Sierd has already mentioned this, that surface processes would also have a very strong impact on resulting style of deformation. So, for example, here in the model without erosion and with erosion, you will see that without erosion, we have more distributed deformation and more localized deformation in case of erosion is implemented. And expectedly, sedimentation has the opposite effect. Once we have intensive sedimentation, we will have this zone of no localized deformation, but in contrast, without sedimentation, this area will be intensively deformed by this faulting. Therefore, implementation of surface processes is extremely important. And normally, this modeling of surface processes is done based on this simple equation where change of topography is controlled just by diffusion of the surface and also by this fluvial erosion described by so-called power stream law. And this is example of the model FastScape, numerical model which implement hill slope processes and fluvial processes, and we can reproduce in this model such nice topography which looks like in nature. But the problem of all these landscape evolution modeling studies is that we should not forget that in this equation, once we take into account tectonic component, we need to implement tectonic uplift or tectonic subsidence, so somewhat coming from deep earth. But in all purely landscape evolution, purely geomorphologic modeling studies, of course, this tectonic component is prescribed. So it could be constant, it could be variable in space, it could be even variable in time, like in this study, but it is always prescribed. But to avoid this prescription of this parameter, we need for coupling between this code for landscape evolution and geodynamic code. And here you can see the result of implementation of such coupled approach, where I have coupled tectonic or geodynamic numerical code with geomorphological code, where you can see that actually we calculate simultaneously deformation in the crust and in the lithosphere and topography at the surface, and both processes are modeled together, and feedbacks in both directions are taken into account. So here you could see some general results of implementation of such coupled approach. And what is important, I will not focus on particular results, but the important is that we can reproduce not only topography, not only surface uplift rate in these models, but we can also calculate synthetic ages, such like synthetic thermochronological ages, such like, for example, apatite fission track age. So it means that in our model, we track the patches of our markers, PT tracks towards the surface, and based on these tracks, we can evaluate the age which corresponds to, for example, apatite helium age or apatite fission track age, whatever. So it means that we can reproduce in our models synthetic or modeled ages of synthetic thermochronological ages, which can be in certain cases be compared with observations. For example, in this study, we apply this 3D geomorphological geodynamic model, where we model this complex system of subduction of asymmetric indenter in the Alaska area. This indenter is bounded by transform faults, so you see that this structure is evidently asymmetrical and require 3D modeling approach. And here we model topography, which is asymmetrical naturally. We reproduced some thermochronological ages, exhumation depths, etc. And we have a possibility here to make the direct comparison of our fully coupled and true 3D geodynamic geomorphological models with observations. So it is just our first results in this direction. And I would like to finish with a few words on the perspective. As I told you that landscape evolution modeling is based on this relatively simple equation. So this landscape evolution is surface processes are always in between. They are impacted from one side, this tectonic component. They are impacted by deep earth processes. But what is important is that they are also impacted by climate. Because if we look at this K parameter in this fluvial erosion component of this equation, you can see that efficiency of erosion is controlled not only by properties of the rock, but also by precipitation, by amount of water falling from sky. So it is amount of rain. So therefore, again, landscape evolution modeling, we use some prescribed precipitation distribution in space or in time. But what we should do to make important step forward, it is just to try to couple this landscape evolution modeling approach with climate models, regional or global, just to have this system coupled, just like we have done it for coupling of geodynamic and surface process modeling. And I will finish that actually in Earth system, we have four principal components: mantle convection, tectonic forces, erosion sedimentation, and climate. So it is deep earth component, surface process component, and atmospheric component, if you want. And for each component, there are already well-developed modeling methods. It is global model convections, these geodynamic models at the crust and lithospheric scale. And also there are a lot of very good models of surface processes, including erosion, sedimentation, probably not only fluvial, but also glacial erosion, etc. And of course, climate models are also very well developed now. And actually what we have already done now by my intermediate scale approach for geodynamical modeling, we have coupled these two units. Then when we couple this with erosion and sedimentation processes, we have included third component. And actually what we need to do, it is actually couple our geodynamic geomorphological models with the paleoclimate models. And I would like to finish my presentation with this very simple and somewhat old-fashioned, but in my opinion, still actual model of the Earth, which can be interpreted in such a way that actually our understanding and knowledge of Earth is based on three elephants. First one is tectonic and geodynamics, or solid Earth, then surface processes, including erosion and sedimentation, and of course, atmospheric processes controlling climate of our planet. And if we put all these three elephants in torch of fully coupled and self-consistent modeling, our understanding of our planet will be significantly improved. So thank you for your attention.
Thank you very much, Alexander, for the amazingly mind-blowing and good presentation. And now I ask the audience here in the auditorium whether they have a question. Marty, please, and Marty, use the microphone because this will help Alexander to hear your question.
Thank you very much. It was excellent. For me, who looks the rocks in a petrological and geochemical point of view, I'd just like to add a comment for the Eastern Branch and Western Branch volcanic rock compositions, which is in good agreement what you revealed about the asymmetry, because the Eastern Branch ones are rich in sodium, and calcium. And relative to this, the Western Branch volcanic rocks are rather potassic, ultrapotassic. What does it mean? The ultrapotassic ones must have been generated from deeper parts of the lithosphere. And I'm talking about melts that are related to the very early stage of the rifting. So what does it mean by geochemical point of view? Is that the Western Branch volcanoes formed at a lithospheric depth of about 3 GPa, where the pergosite is no longer stable. That's why the ultrapotassic manner. And in contrast, the eastern ones are rather formed in the stability field of pergosite, according to our calculations, at 2.5 GPa, so a little bit shallower depth. So there should be, what we do believe is that there is an asymmetry of the lithospheric thickness in between the Western and the Eastern Branch. So I just wanted to add this comment, which is a good agreement, what you just revealed by your model. Thank you.
Yeah, thank you. Yeah, that's a good point.
Is there any more question? You see it?
Great presentation, Alexander. Very, very interesting. Also, the prospects for the future. I have a question concerning the East African Rift. I noticed very different prediction for the topography for the Western branch and for the Eastern branch. And in that context, how does the model compare, let's say, with information from the basins and from the rifts in terms of subsidence and uplift? Have you looked at that?
Yes, we have looked at this, and again, first order features of topography are reproduced indeed relatively well in our models, but to do it better, indeed, we need to work on coupling of this modeling with surface processes, which was not yet done for this particular East African Rift models, because we have tested this approach in a rather convergent system, but it is this what we should do actually. Yeah.
So you expect basically that the East African Rift system will be a prime area to make this next step that you discussed at the end of your talk?
Yes, I think that it is one of probably the most perspective areas because it is indeed a process of ongoing opening of a new ocean, and I think that it is one of area which we can use this approach, even if in general people prefer to speak about convergent setting in the context of this coupled geomorphological and geodynamical approach, just because there we have more pronounced topography response, and it is more simple to see this response in thermochronological data. But I know that for East African rift systems, there are also several new studies devoted to getting new thermochronology data, and I think that we can also apply this approach for this region just to see how well we can fit these new observations as well.
Great. Many thanks again.
Yeah. Is there any more questions?
Yeah, from my side, again, congratulations. I like you talk very much. Just maybe a little bit delicate question. Just recently I have seen a model of Pietro Sternei on the Ethiopian part of the rifting, and he emphasized very much on the very large difference in precipitation on the western versus eastern part of this rift system. And even he, as far as I understood, he even stated that the distribution of surface magmatism practically, as far as I understood, he said that is controlled by the amount of precipitation. How do you consider this concept, or what is your opinion, if I can ask something?
Yeah, I am fully agree with Pietro, because indeed not only surface distribution of deformation, but also magmatism can be controlled by surface processes. And what Pietro has done is done only in 2D, but actually it is our common common task to extend it in real 3D and continue the direction. Yeah.
Thanks.
Okay. Yeah.
There is no more question from the audience here. I'm just looking the chat window if we have any comment or question from the online participants, but I see no question coming from there. Okay, so thank you, Alexander, again for the nice talk. And now I would like to ask Alessio Lavecchia to turn on his video, and I hope that you are here.
Yeah, I'm here.
And,
Okay.
Okay, Alexander, and okay, excellent. So we have the presentation. So Alessio is a Italian colleague who did his PhD at the Utrecht University and then moved back to Italy. And Alessio, please just correct me if I'm wrong. You moved back to Bari, where you're currently working with INGV, and Alessio is also concerned with geodynamic modeling with special emphasis on volcanism and magma generation. And today he's going to present a very interesting thing about the Gargano earthquake in Italy. So it's especially interesting for the seismologists, and we are very much happy to have you here, Alessio, with us. So please give your talk.
So thank you very much, István, and good morning to everyone. Yes, I work for the National Institute of Geophysics and Volcanology, but right now I have a position as a researcher at the University of Bari. And today I would like to talk with you about the Gargano Promontory, which is an area where we recently installed a new seismic network. And when we started to record the microseismicity in this area, we had quite a few surprises because there is a very peculiar seismicity pattern. We did not expect that. And the study is basically centered on the causes that could have generated this seismicity pattern that we will see in the following slides. So to give you a very quick overview about the Gargano Promontory, this is part of the Apulian foreland. And this is the foreland of the southern Apennines. You can see it very well in this figure. From a more geodynamic point of view, a more wide overview, this is part of the Adria microplate, which moved coherently with Africa at least until late Miocene during the Eurasia-Africa collision. After late Miocene and during the development of the Balkany system, the other microplates started moving independently, and its movement passed from clockwise to counterclockwise. This reflects also on the geodynamics of the Gargano, where we switch from first phase of extension during Cretaceous and Paleogene to a phase of compression and uplifting during the late Miocene, which seems to be still on. Although it has quite a few peculiarities that if I have the time, I will explain you better afterwards. If we consider nowadays the division of the Adria microplate, we see that probably it's not anymore a single microplate, but it's probably divided in two blocks. One is the Northern Adriatic microblock, and the other one is the Southern Adriatic one. And it seems based on seismic and GPS data, especially GPS data, it seems that the movement is not the same anymore. While the Adria microblock is almost motionless and its movement is quite coherent with the surrounding plate, the Southern Adriatic block has a movement on its own with a strong counterclockwise movement component. In the Gargano Promontory, we see mostly carbonatic rock uplifting, outcropping. This is basically a paradise for all the carbonatic sedimentologists because you can see all the fascias going from deep water carbonates to lacustrine carbonates. But these are not the only rocks outcropping. There is a small outcrop of mafic rocks. I will tell you more in the following slides. So, and in my opinion, this is a very important point. From the seismic point of view, the Gargano has always been considered as an area of low seismicity. And if we think about it, this is not surprising because a little bit west of it, we have the Southern Apennines, and south of Gargano, we have the Calabria Peloritani Arc, where the most, if not the most destructive earthquakes in Europe, among the most destructive earthquakes in Europe occurred here. You just have to think about the 1908 earthquake in the Messina Strait with a magnitude of 7.1 and an intensity of the 10th degree on the Mercalli scale. Saying this, it's not true that Gargano is a low seismicity area. We had in historical times quite intense earthquakes. Just to give you an example, the one of 30 July 1627 with a magnitude of 6.7. And this has been very well documented in historical recordings. Just a little curiosity, if we consider the historical seismic catalog in Italy, Gargano is the place in southern Italy where we have the most ancient catalog. It is considered to be complete, start from the 16th century, whereas in other areas in southern Italy, you need to go to the second half of the 19th century to consider the historical catalog complete, at least for earthquakes with a magnitude higher than 5.5. Despite this, despite the knowledge that we had in this area for historical earthquakes, until 2012, we had only 3 seismic stations in a radius of 200 kilometers of the Gargano. And if we enlarge the area to 300 kilometers, we had 5 seismic stations. So we absolutely had an insufficient coverage. The situation changed drastically in 2012 when we installed a new network of 12 seismic stations. And in this way, we started to have a remarkable coverage. So as soon as we started recording, we already saw that the earthquakes were not uniformly distributed within the crust, but they have a sort of bimodal distribution. So if you observe the histogram in the panel B, we observe a first peak of activity at a depth of more or less 7-8 kilometers. And this peak refers to an area southwest of the Gargano Promontory. You can see here these green dots. If we go deeper, we have a second intensity peak, which is actually much more pronounced than the first one. And this one affects the entire Gargano area. It's basically distributed along the plane, which seems to be gently dipping northeastwards. And the difference between these 2 peaks is in regards, first of all, the focal mechanisms, because the focal mechanisms of these shallower peaks, shallower earthquakes over here seems to suggest extension, whereas the earthquakes which are deeper seems to have focal mechanisms suggesting compression, or at least with a strong compressional component. Another difference that we need to mention is the correlation between seismic activity and heat flow. In the entire Gargano, we have a cold situation where the heat flow at surface does not exceed 40 milliwatt per square meter. But the situation southwest of the Gargano is completely different. Here we have what's called the Candelaro Valley, where the Candelaro River flows, and the heat flow in this area can even exceed 100 milliwatt per square meter. So if we consider this data, we observe that the Gargano Promontory is one of the few regions across the globe where the seismic activity is concentrated in the lower crust, especially microseismicity, but not only microseismicity. I would like to give you a very fresh data. Today at 9:30 in the morning, there was a earthquake in the Gargano with a magnitude of 2.8. So very fresh data. And the striking part, at least for me, was the fact that we have this seismicity here concentrated between 20 and 30 kilometers of depth. But above it, we have basically nothing. And so we have something that which is generated within the lower crust. But if we consider the classical Christmas tree diagrams, we should consider the fact that according to these models, lower crust usually deforms by ducted flow, whereas in order to have seismicity, the rocks have to be brittle. So we were wondering, how is it possible that this occurs in the Gargano? In order to do this, we build up a numerical model that takes into account the lithologies nowadays observed in the Gargano. So we based our lithological structure on seismic reflection data and well data from mostly from AGI, but also from Konoko. These are wells digged in, let's say, second half of the 60s and 70s and 80s. So we have a first layer of sedimentary cover, which is divided in one layer of carbonates, which overlies a layer of dolomites and anhydrites, and a layer of thermotriassic sediments. The sedimentary cover lies on the top of the basement, which is composed of upper, middle, and lower crust. For the upper crust, we have put rocks which are a mix of felsic granulites and micacists. For the middle crust, we have inserted granodiorites and tonalites, whereas for the lower crust, we have inserted a mixture of felsic and mafic granulites, coherent with other areas in southern Italy where the basement is outcropping. Our model is steady state and takes into account the radiogenic production and temperature dependent density. Here you can see a few values that we have adopted for our model. Regarding the geotherm, which has been implemented, it takes into account essentially two temperatures at the base of the crust, 450 and 500 degrees. Sorry if I go a little bit down, but in this H pattern, we have considered areas where we could have fractures and presence of fluids within the rocks, mostly water, and where these fluids are implemented, we take into account it in the thermal model by multiplying the thermal conductivity by a factor of 3, which is appropriate for rocks which are saturated in water. Regarding the rheological behavior, we have considered the Coulomb-Navier criterion for the brittle behavior when one of the stress axes is perpendicular to the model. And this location creep for the viscous behavior. Regarding the Coulomb-Navier criterion, you can see here where the fluids exert their own effect. We multiply basically the lithostatic pressure by a factor 1 minus lambda, where lambda is a post-fluid factor. And in our model varies between 0.4, where we consider fluids at hydrostatic conditions, and 0.8, where we consider our fluids at near lithostatic conditions. For the dislocation creep, as I said before, we have considered a mixture of rocks for the layers, especially composing the basement. Usually we don't have these values of rheological parameters for each single rock, but we mostly have them for minerals. So what I did was to apply these two different ways for averaging the rheological parameters for rocks, starting from the parameters for each single mineral. We have essentially two ways to calculate it. One is the Reus average method, which is appropriate for equigranular rocks such as granites or tonalites. And the other one is the Voigt average, which is more appropriate for rocks which are rich in matrix, such as the micaceous, for example. Of course, we don't know which kind of rocks we have at depth, which kind of structure of rocks we have at depth. Therefore, I applied an iterative method that I didn't insert here, but it's well described in paper G. et al. 2003. If you're interested, just tell me and I can give you the precise reference. So I would like to start from a situation where we did not insert a fracturing of rocks, or we did not insert fluids. We just consider this part of the model left of this red dashed line in extension, and this part of the model in compression, coherently with focal mechanisms of the seismicity that we have found. If we see here, most of our model is ductile in the basement, the crystalline basement, and brittle in the sedimentary cover. The red dots are the hypocenters, and we see that there is basically no correspondence between the behavior, the rheological behavior of the rocks and the position of the hypocenters. So we have tried to insert fracturing of rocks without the presence of fluids by decreasing the rheological parameters for the brittle behavior. And we see that we have, especially in the area where we have extension, where rocks are subjected to extension, we have a sort of a deepening of the brittle ductile transition. We have the appearance of the thin brittle layers within the basement, but still we have no correspondence, especially where we have rocks subjected to compression. We also have measured the surface heat flow in our model. And we have calculated values which are around 40 milliwatt per square meter. This is a value which is coherent for the Gargano Promontory, but absolutely not coherent with values that we have measured southwest of the Gargano. As I said before, values can exceed 100 milliwatt per square meters. These models are based on a geotherm, which gives you a temperature of 500 degrees at the base of the model. So in the next suite of simulation, I increased the value of the pore fluid factor, arriving up to a value of 0.8 in the hatched areas here. And we see that in rocks subjected to extension, we have a significant deepening of the brittle ductile transition. Most of rocks are brittle. And there is a good correspondence, especially with the upper cluster, the one which is subvertical southwest of the Gargano. Regarding the region of the model, which is subjected to compression, however, we still don't have a correspondence. We have the appearance of this thin layer of brittle behavior, but this is absolutely insufficient to justify such a pronounced seismicity in the lower crust. Regarding the value of heat flow, we finally managed to arrive to values higher than 100 milliwatt per square meter in the areas where fluids occur. And this is a good correspondence, but still maybe they are a little bit too high, because the values that we measured are around 110 milliwatt per square meter. So what I thought is, okay, let's try to decrease the temperature at the base of the model. So let's try to consider a colder geotherm within the crust. And the results that I obtained are illustrated in the upper panels. We see that finally we managed to obtain a very well-defined layer of brittle behavior within the lower crust. We have sort of a better correspondence between brittle behavior of rocks and the position of the hypocenters, and also the values of surface heat flow correspond very well. We have 35, 38 milliwatt per square meter in the entire model, except in the area where we have fluids, where we have 100 milliwatt per square meter. And these are perfect values for what we have seen in the Gargano region. However, the thickness of the brittle layer within the lower crust maybe still a little bit too little. We would like to have a thicker layer where brittle behavior occurs. And we were thinking about how to obtain this thicker layer. So we had two possibilities. One was to increase the thickness of the lower crust, and the other one was to change the nature of the lithology of the rocks within the basement. And how did I change the lithology of the basement? I inserted some mafic rocks inside. As I said before, most of the rocks outcropping in the Gargano are carbonates. But north of the Gargano, there is an outcrop of mafic rock with age, say early Paleogene, within 58 and 62 million years. which have, by the way, a strong plume geochemical overprint. Gravimetric study in the Gargano also highlighted the presence of several mafic layers within the crust at various depths. So I thought that it was absolutely reasonable to add these layers within the basement. And I had up to 30–35% of mafic rocks within the basement. And both results gave us good results. Both choices gave us good results. In my opinion, from a geological and geodynamic point of view, it's more coherent to insert these mafic rocks within the basement. So at this point, a question is, how did this fluid reach this great depth within the Gargano? When we observed the setting of this two cluster of earthquakes, we do not really see a communication between these two vertical vertical cluster southwest of the Gargano and this layer where seismicity is concentrated within the Gargano itself. And thinking that the fluids can travel all the way from surface to a depth of 20 or even 30 kilometers is maybe a little bit too much to think. We don't have any evidence of that. In addition, we don't have any seismic evidence of movement within the Gargano upper layers up to the middle or upper crust sedimentary cover. This seems to be completely aseismic. So an hypothesis I'm working on right now is the fact that the fluids can arrive from below. We are testing together with István the possibility that small plumes can be subjected to the gassing. And if we consider the Gargano mafic rocks outcropping in this outcrop here, Punta delle Pietre Nere, this has been considered as part of a much larger magmatic province that affects the entire Europe and goes all the way from Canary Islands to Turkey. This is a magmatic province that has more or less the same age. It tends to get younger from the Canaries to Turkey. It has been called Circum-Mediterranean and other Cenozoic igneous province. It seems to have been caused by some diaperic instability, or probably in the case of Punta delle Pietre Nere, baby plumes. They have a strong IMU oceanic island basalt component. And if this is true, there is no reason to believe that such an upwelling cannot act today. In my opinion, this is a much more coherent explanation for the presence of fluids. Especially these upwellings are cold, but they are hydrated. They will start liberating volatiles and generating volatiles, CO2 and especially water, even at considerable depth. So we are working on models that can generate these volatiles. I hope that I will be able to tell you more in the coming months. So to conclude, I would say that the seismic activity in the Gargano is not the result of a single factor. We have to consider several different mechanisms to justify it. Surely the lithological structure is important. The cold temperature within the Gargano is also quite important. But in our opinion, fluids have played a key role. And I personally believe that they can be generated by the gassing of small diaperic upwelling within the mantle. Also considering the upwelling of the uplifting of the Gargano itself, which is accompanied by a general subsidence of all the areas around, seems to be very, say, punctual. But once again, I hope that soon I will tell you more about it. So thank you for the attention.
Yeah, thank you so much, Alessio. And the question is if there is any question, but Csaba is already raising his hand. Gábor, can we have the microphone for Csaba? Yeah, okay.
Thank you very much. It was a nice talk. My question is related to your model. What fluid did you use in it?
Sorry, I couldn't hear.
Sorry?
I couldn't hear your question. What did I use it?
Yeah, probably it's not on, but the question was that what kind of fluid did you assume in your model?
Regarding the area subjected to fluid presence. It's mostly water. I would like to insert values relative to CO2, but right now I don't have the right data. In the future, I'm working on these petrological models, and I really hope that in the future we will manage to include also CO2.
So it's liquid H2O, am I right?
It is liquid H2O.
Yeah. Thank you.
Although we can imagine that at that we are also switching from liquid to superfluid conditions.
Okay, thank you.
You're welcome.
Is there any more question? Gabor?
Just a quick one as a side note, you mentioned this 100 milliwatt per square meter area along the fault. So does it have something to do with the fluids coming up along this fault, or what's the explanation? Because we are in the foreland and this is a very high number for geothermal kind of a signal.
It can be that it's due to the fact that we have fluids there and we have some sort of circulation of fluids from lower levels of the crust up to the surface. Unfortunately, this is a very badly studied area yet. We are reviewing all this catalog, and it's also difficult to measure heat flows there. But the few data that we have suggest heat flow of 100 milliwatt per square meter. We do not have any evidence of magmatic bodies buried underneath, also because, as we have seen in the surrounding areas, the values of heat flow are quite low. So we believe that it's fluid circulation within the crust.
And I also ask the online participants if there is any question, please use the chat window. And I also ask Gabor in the back whether you see any question there in the chat window, because I hope we really want to take all the opportunity. Okay, there's no question. Alessio, one question from my part. So did you actually try to correlate the depth of the earthquake with any metamorphic phase transition like dehydration, amphibolite, granulite phases during this modeling?
This is something that we were also discussing with other petrologists. It is possible that we are having some metamorphic reaction which are generating fluids, but I think it's unlikely because the most intense tectonics in this area, it's quite old. So in my opinion, the fluids had all the time to get, let's say, generated and to leave the system. So it's quite difficult to believe that fluids are still there. But this is something that probably needs to be also studied from a more quantitative point of view. So far, I don't believe that we have actual reaction occurring in this area.
Okay, thank you. So if there is no question, then thank you very much for the excellent presentation.
Thank you.
And now we are going to have a technical break for lunch. And I asked the online participants because we are more or less on time, but you know, I think we need that half an hour. So we will probably start 5-10 minutes late. I will also announce that in the chat window. So people who turn up, they will realize that we are a little bit late because I think deserve this time for this break. And also I just would like to ask you that when we return for the first afternoon session, I think we should have a group photo here with the online participants because the weather is not really charming outside. So I think it's just better to stay inside. So when we show up, then we will make a group photo. So please be reminded. And also I need to announce a very positive announcement that our director Viktor was very kind and generous, so he offered us a nice pizza for lunch, so it's probably waiting for us. So please take the pizza, and after be mentally prepared for the afternoon session. And thank you very much for all the speakers, and also for your active participation. Yeah.